everyone, welcome you all. And today's topic is all about problem solving on switch level modeling. It's a part 2. Okay, so far we have discussed various problem solvings on different levels, right? In the Verilog we have, as we know that in the Verilog we have 4 levels of modeling styles. We know that first one is all about the behavioral modeling. The second one is about the data flow. The third one is about the gate level modeling, and the fourth one is about the switch level modeling. So in the problem solving concept, already we have discussed about few problems on behavioral modeling, few problems on data flow modeling, few problems on gate level, and now we are going to discuss few problems on switch level modeling. Okay, so what is a switch level modeling indeed? So switch level modeling is nothing but it is a kind of modeling style in the Verilog where all sort of the switching between the different elements can be done with respect to the different switches. Okay, so in the switch level modeling we have come across many different types of switches like bidirectional switches, unidirectional switches, transistor switches, and so on. So now we will discuss something about bidirectional switches. So what does this bidirectional switches mean? Bidirectional switches is nothing but the flow of current and voltage. It takes in two-way of, okay, the two-way of passing of the transistor, passing of the current and as well as the voltages is nothing but the bidirectional switches. And now, you see in this particular class, we will be writing, we will be discussing more about how to write a particular code with respect to the bidirectional switch. So as we are discussing the bidirectional switch, the code with respect to that sort of bidirectional switch goes like this. To instantiate bidirectional switches, in the coding part, in order to instantiate, okay, to represent this bidirectional switches, I have to write like this: trans. Okay, trans is a keyword, the instance name followed with instance name and then the port list. So we know this, the mechanism, right? So we know the mechanism of how to begin our code with respect to different by using different keywords, right? So here, as we are discussing about the bidirectional switch, tran is one of the bidirectional switch, and the keyword pertaining to that bidirectional switch is represented as tran. Tran followed with the instance name and then the port list. So the port list consists of input and as well as the output ports. So here tran is a bidirectional switch. So here in the bidirectional switch tran, we have tran I0 and tran I1, right? So here, so if you see the second statement and the third statement here we are writing like tran if 0 and tran if 1, right? So tran if 0 and tran if 1 are nothing but the two switches which are under the tran switch. So tran if 0, okay, tran if 0 is a bidirectional switch where the keyword follows with the tran if 0, and the instance name, see here, in the instance name is nothing but it is a name of a switch that you are mentioning. Okay, when you're writing the code, it doesn't matter if you don't mention the instance name. Okay, it is our wish whether to represent or not. So the tran if 0 instance name, this is an optional. Okay, you can consider that instance name is an optional. So tran if 0, and in the input and output ports, we must write, or else we must instantiate what are the inputs and what are the outputs and as well as the control lines, right? So in, out, and the control. And then followed with the second, the third statement goes with the tran if 1. Okay, tran if 1 is followed with the instance name. Again, it is an optional, and then followed with the in, out, and control signals, right? And then instance name is optional. See here, the clear statement is giving that this instance name is optional. That is, it doesn't matter if you don't write here in the code, it doesn't matter. And if you mention the name of that particular gate as well, it doesn't matter. Okay, so this is what this the instance name is optional. And then if we observe, these are the 3 figures based on the bidirectional switch. So the bidirectional switch, the first figure is all about RTRAN. Okay, RTRAN is a bidirectional switch where it has the input and the output. Okay, and then the second one is about the category of with respect to 1 and then with respect to 0. So the tran if 1 goes with input, output and as well as the control line. Okay, based on the control line we can able to obtain, or as we can able to switch on the particular state of the particular state. Okay, if tran if 0, sometimes based on the control signal, if control signal is 0, what happens is the switch goes on. If control signal is 1, the switch goes off. Okay, the switch goes off. So this based on the control signal, the PMOS and the NMOS transistor, the switching of the enabling of PMOS and NMOS transistors works on. Okay, so that's the reason in this in the bidirectional switches, it is major thing we need to remember is in the port list we must represent what are the inputs and what are the outputs and as well as the control signals. Then the third figure is about the tran if 0. So the tran if 0 is nothing but we have input, we have output and as well as the control. So if you observe this tran if 0, see there is a node, right? So it is a node. So that's a differentiate. That's how we will differentiate the tran if 1 and tran if 0. So these are the basic bidirectional switches where we use most in the Verilog. Okay, and then we move forward. So coming to the delays. So as we know that delays are nothing but they go as per the time, right? So the delays go with respect to the time. Sometimes what happens is at the output, the delays, they plays a very crucial role when you transfer the data from the input to the output. Based on the delays also, we can able to get the appropriate output as well. And now in the delays, we will discuss how the delays works on with respect to the unidirectional switches. So these are the unidirectional switches. The unidirectional switches are nothing but the transfer of the flow of current and voltages, they goes only in one directional. Okay, that's the name. We are saying that it is a unidirectional switch. Okay, and now unidirectional switch with respect to the delays, how it works, we'll discuss. Now, specify no delay. Okay, the first one is specify no delay. So in the specify no delay, we can write. Okay, we can write the instantiation of a particular switch is a MOS switch that we are considering. Okay, MOS switch, name of the switch MOS. MOS is nothing but it is a keyword. So remember that in all the 4 levels of modeling styles, okay, behavioral modeling, switch level modeling, data flow modeling and as well as the gate level modeling. In all these 4 levels of modeling, instantiating the keywords is a major role, right? Major thing to remember. That means what? Instantiating the keywords. There are special keywords to be mentioned for the some kind of leveling. Okay, so here when it comes to this unidirectional switches in the switch level modeling, so for like in the previous classes we have discussed, I think in the module 5. In the module 5 we have discussed different types of switches. Okay, for example, let us consider NMOS switch. So for this NMOS switch in the coding part, okay, when you're writing your program, you have to remember that not to forget to write the keyword. Okay, that means what? If you are considering the NMOS transistor or as NMOS switch, remember that your code should start with NMOS keyword. Okay, it is a keyword, right? And if you're considering your switch as PMOS, okay, if your switch is PMOS, then remember that your code should start with a keyword called PMOS. And if you're considering your switch to be a CMOS, remember that the keyword or is the keyword that you have to follow is CMOS. So these are very, very, very important in point of writing the keyword, writing the code. Okay, that's how we are representing here. In terms of delay, this is the codes with respect to the unidirectional switches in terms of delay. And now MOS is a keyword, that is metal oxide semiconductor switch I'm considering. So my keyword should goes with MOS. Okay, instance name, this is an optional. Whether you give the name of this particular switch, whether you represent or not, it doesn't matter. Okay, it's an optional. Then follows with the port list. In the port list, you have to mention the input, output and as well as the control line. So as we are discussing about the delays, And now we will see in the unidirectional switch how this delays act, or else how the importance of this delays considered to be in the unidirectional switch. And then this is specify no delay. So here if you observe in this first statement, there is no specified, the specification of delay is not mentioned. So that's the reason our heading is of specify no delay, right? And then goes with specify propagation delay only. And so the second statement we are talking about, we are specifying the propagation delay. So how we are specifying? See, delays are mentioned, delays are instantiated with respect to the hash, right? So MOS switch hash propagation delay. So this is nothing but the instance name. So whether you represent this instance name, it doesn't matter. As I said you, it's an optional thing. So propagation delay, and then instance name, input output. Okay. Then specify both rise and fall times. So when we are discussing the topic delays, we have come across this such times, right? Rise time represent with TR, fall time represent with TF, and we have one more time as well. Okay, that is turn off time, right? Turn off time. So these are the three basic times that we have come across when we are discussing about the delay. So what is a rise time? TR time is when the propagation is taking place from 0 to 90% of the delay. Okay, from 0 to 90%, that is from 0 to 1. This is nothing but the rise time. And fall time is when it's taking its curve from 1 to 0. Okay, it's falling down, right? From 1 to 0, then it is nothing but the false time. So, here we are specifying the propagation with delay. This is how we are representing. And if you are specifying both rise and fall delays, okay, rise and fall times, then here MOS switch T rise and T falls. Okay, T rise and T falls, two particular delays we are representing, rise time and fall time, and instance name, and also the port list. Then finally specify rise time, turn off time, and the fall time as well. So here we can write our code with respect to specifying the delays, and also with respect to of how many delays that you are specifying. Sometimes there is a possibility of specifying only one delay, okay, right? TR. And sometimes there is a possibility of specifying two delays, TR and TF. And some other situations we have come across to represent the three delays, that is TR, TF and T on, turn of time. Okay, turn of time. So this is how the representations takes place in terms of delays with respect to rise time, fall time and turn of time in the unidirectional switches. Okay, now we'll discuss about the bidirectional switches as well. So these switches do not delay signal passing through them. So these are bidirectional switches, right? So bidirectional switches. So the communication between the communication happens with in the two-way. That, right? That means what? The propagation of the current and as well as the voltage, they can consider to be in a two-way. So these switches, they do not delay signal passing through them. So as these are the bidirectional switches, we are saying that there is no delay signal which is passing through them. Okay, now we will see how can we specify the delays with respect to this bidirectional switches. So instead we have turn on time and turn off time delays while switching. So we have turn on time and turn off time, right? T on and T off. T on time will have rise time and T off time will have fall time. Okay, so to specify no delay. So here also in this the specification with respect to no delays, and with respect to turn on and turn off delays, and with respect to separately instantiating the turn on, turn off delays. Okay, so here we will see how we will specify all such delays. So now when we specify no delay, we say that this is the name of a this is a bidirectional switch, BDSW, and name of a switch, and instance name is an optional, we all know well. And then the port list representing the input and as well as the output ports. So in, out and control. And then specify a turn on and turn off delay. So here in the second statement, we are specifying two times, that is turn on and turn off delays. So here In this case, how can we write our code is the name of the code bidirectional switch followed with the name. See, turn on instance in out control. Okay, so here we are representing turn off. In the same way, we can also represent for turn on like this: bidirectional switch name followed with a delay. Here we have mentioned turn off, right? So now I can also mention the turn on time. Turn on separately and turn off separately. Okay, so that is what the third statement says. Separately specify turn on and turn off delays. So how can we specify separately is, say like this: bidirectional switch name, turn on and turn off. See, here we are separating, comma is nothing but we are separating the two times. One is on time and one is off time. If you want to instantiate or specify the separate times, then you have to go with a comma. Or else if you want to specify both the times in one way, okay, in one shot, in one stretch, if you want to specify both the times, then you can specify by not giving any comma, without differentiating them, you can specify like this: T on and off. Okay, so this is how we can specify the delays in the bidirectional resistive switch. Okay, so what is this resistive switch? Resistive switch is one of the switches that we have discussed in the earlier. So resistive switch we are representing with R-tran. Okay, we know that tran is one of the basic switch. These are the bidirectional switch, right? So R-tran if 0 and R-tran if 1. Okay, R-tran if 0 and R-tran if 1. These are the basic bidirectional switches. So now coming to the resistive switch. Resistive switches are nothing but the MOS and the CMOS. Okay, metal oxide semiconductors and CMOS semiconductors are bidirectional switches. MOS and bi-CMOS switches are the bidirectional switches, and they can be modeled. Okay, they can be modeled as corresponding resistive devices. We can model the switches with respect to the resistive devices. That's the reason we are representing it with the R-tran. So this particular switch is nothing but a resistive switch. So here, if you observe this particular table, we see the MOS, CMOS and bidirectional switches. So the MOS, CMOS and bidirectional switches, for the MOS switches, we are saying that one is RNMOS and RPMOS. So this MOS switches are nothing but the resistive switch, and the representation of the resistive switch goes with respect to the NMOS and PMOS as R. Okay, that is resistive NMOS and resistive PMOS. And then if you are considering the CMOS switches, okay, complex metal oxide semiconductor switches. So in that case also we can represent, or else we can relate it with the resistive switch as RCMOS. Okay, and then finally the bidirectional switch. So the bidirectional switch are in terms of resistive switch, how can we write is R-tran if 0 and R-tran if 1. Okay, so these are just the representation of the resistive switches. And coming to the signal strength. So the signal strengths are nothing but based on the strength of a signal. Okay, based on the strength of a signal, the value can be given, and based on that value we can segregate, or else we can easily consider, or else we can easily tell that what sort of the degree that particular signal is having. So this is a small table based on the signal strength and the category where it goes. Okay, so the CMOS, we know that the MOS, CMOS are the bidirectional switches, and so they are corresponding to be called as the resistive switch. And this is a table. Based on this table, we can analyze easily that what is a degree. Okay, what is a degree of that particular signal. So coming to the signal, we have coming to the strength, we have supply strong, pull weak, pull large, weak, medium, high scale. So these are the ranges. Okay, so these are the categories in the strength. Okay, categories of the signals with respect to the strength. And coming to strength 0. Okay, when you are applying for 0 strength, then all will goes forward with the 0. And if you are coming up with the strength 1, then all will be followed with the 1. And then finally the type. Okay, now we will, in the fourth column, we will be deciding what sort of this signal is. Okay, so now supplies are strong. See, supply, strong and pull. So these three comes under the driving type. Okay, and large is nothing but the storage type, and the weak is also a driving type, and then the medium and small are storage as well, and then high impedance is simply the high impedance. Okay, and now coming to the degree, okay, based on the type, now we can able to give, or else we can able to label it as for regarding the degree. So the strongest from the weakest to the strongest, that means what, the very weakest signal that I can say is a high Z. Okay, and the very strongest signal that we can say is a supply. Okay, the supply, the strength of a particular thing, or else the strength of a particular signal with respect to the supply is nothing but the strongest signal, and the strength of a signal with respect to the high Z is nothing but the weakest signal. So based on this signal strength, we can able to know what sort of degree is that particular signal is having. Okay. And now we will see the signal contention. So the signal contention is nothing but multiple signals with same value and different strength. So here the contention, how can we differentiate the contention between the signals is, some signals say we have different multiple signals will have. Okay, the multiple signals with same value. Okay, that means what, we have S1, S2, S3, S4. So these are the multiple different signals, but the value are of same 0, 0, 0, 0. Okay, and with different values. Okay, different strength. See here, they have the same value, but the different strength. The different strength is nothing but, the strength is nothing but, sometimes S1 may be a weaker, S2 may be a stronger, right? So that's what the different strength. Many multiple signals though we have, but it all depends upon the different strength, and that strength also depends with respect to the same value as well. And now we have, see here, two signals, SU1 and PU0. Okay, so these two are content, and finally I'm getting SU1, right? So the multiple strength, these two are the multiple signals. They have some different strengths, but finally when I club these two signals, I'm forming, or else I'm getting into a single strength. Okay, single signal with that signal may have same value, but they may go with the different strengths. Then multiple signals with opposite value. See here, they have the opposite value, right? PU0, PU1. See, these are multiple signals, but they have what, 1 and 0. See here, these are with the opposite values with the same strength. Okay, so opposite value with the same strength is, see here we have different strengths. When we are having a different strength, we'll be getting the output in terms of either 1 or 0. But when you are having a different opposite values, okay, if the values are quite opposite to each other, then the strength goes with the same strength. That's the reason we are representing it with PUX. Okay. So this is about the signal contention. So in the switch level modeling, we have come across, like we will be coming across all such sort of things based on the signals and the strengths, and also the different signal values as well. And now we will see the signal strength reduction. So what is the signal strength reduction is? Sometimes what happens is, from the signals will come from different, multiple signals will be originated from different devices, right? So each and every signal have their own strength. Okay, we can't predict. Sometimes the signal will be a weak, and sometimes the signal may be a strong signal. Okay, so now what happens is, when all the strong signals are accumulated together, then it's responsible to eliminate some signals. Okay, that's the reason such sort of eliminating is nothing but the signal strength reduction. Okay, so signal strength reduction is non-resistive switches do not reduce the strength. So here non-resistive switch, only resistive switch, they have some signal strength, but non-resistive switches, they do not reduce the strength of a signal, except that a supply strength is reduced to strong strength. So usually the non-resistive switches, they don't reduce the strength, only the resistive switches, that is RTRAN, okay, RTRAN if 0, RTRAN if 1, like that. So only the resistive switches, they will reduce the strength, whereas the non-resistive switches, they don't reduce the strength, and also the reduction in the signal strength will also be, they don't reduce the signal strength as well. Okay, so the resistive switches reduce the signal strength as follows. So how the resistive switch will reduce the signal strength is, here see, if you observe, this is the input and it's the output, right? So input we have supply strong, pull weak, large. See, these are the categories, right? So these are the different categories that we have in the input. A signal will have such all this sort of the all such sort of what do we say, the categories a signal will carry. And at the output, it's based on the strength, okay, based on the supply strength and based on the strength of a signal, then we can able to identify what sort of degree that signal is having. Okay, for example, here if you see the resistive switches, the input if it is supply, okay, if input if it is supply, then and if it is concatenating with respect to the strong signal, then the both signal, the output will be pull. Okay, likewise if it is pull directly, will be getting the output as a weak signal. And similarly for the large and weak, if they both are concatenate to each other, then we will be observing as the medium. The signal strength of that particular signal is medium, and so on. Medium and small, we will be getting the particular signal strength. Okay, the signal strength would be small. And obviously high Z strength, okay, high Z signal, if it is having the high Z signal, with respect to the strength will be high impedance, and as well as the strong the degree will be high impedance. So in such cases, I can say that the degree of that particular what do we say, that particular high Z signal is high Z as well. Okay, there is no change. If you observe the previous slide, see here you can see, as these are the categories with respect to the strength, and also with respect to the 0 and 1, what are we saying is the lowest or is the weakest signal that we have in among this all the categories is high Z. Okay, that means what, here you don't see any change. Okay, it's a high impedance value, right? So it's one of the weakest signal if you compare it with all the signal strengths. And then we will see a small example based on the decay. Okay, based on the decay, we will see the module capacitor, register, data and gate. Okay, and then tree reg. Tree reg is one of the nets or is a data type that we consider if you are considering any sort of switches. So tree reg, it is a large signal with a delay of 0, 0 and 50. So here we are considering the 3 times. Okay, 3 T's. So that means you can assume it as a rise time, fall time and turn off time. So turn off time and cap. See, tree reg declaration with a charge decay time of 50 time units delay. So it is that it's nothing but we are just representing, or else we are declaring the tree reg data type with respect to the delay. Okay, right? And then representing the switches NMOS as NMOS1 and cap1 data and gate. So here this is the NMOS. See, this is a keyword. NMOS is a keyword. Why the reason is we are considering the NMOS switch. So NMOS switch that drives the tree reg. Okay, so the NMOS switch is driving the data type called the tree reg. Okay, in the some other examples, I can write in place of NMOS, I can write a PMOS. PMOS 1. Why? Because here I'm considering my switch to be as P transistor. Okay, P switch, PMOS. Then now we will start the code. Initial, begin. This is a monitor, only is meant to display, and then gate data as 1, gate as 1. And now we will see all the statements go as per the delays. So with 10 delays the gate is 0, and 30 delays the gate is 1, and 10 delays the gate is 0, and finally for 100 it is finished. So here toggles a driver of the control input to NMOS switches. So here what happens is at certain point of time it just toggles. Okay, all the signals will toggle like this. For example, a signal 1 is traveling, signal 2 is traveling, signal 4 is traveling. Okay, at T1 they are traveling in a straight forward, okay, without any interruption. At T2 also they are traveling, or else they are just passing by without any interruption. But at certain point of time, what happens is all the transits, all the times, okay, all the signals are toggled. Okay, they are overlapped, or else they are misplaced with each other. Right? So this is what at for example, at 100 nanoseconds of delay, I can say that at this point of time, the toggling takes place. Okay. And finally, end mode. What happens if the toggling takes place is the information, whatever the signals, all these 4 signals are carrying at certain point of time, the informations will be decayed. Okay. It collapse. And then we will see at 0 stage 1 states, at 10 data, it is LA1, at 40 data, ST1, and 50 data, LA1 as well. So here they have given a warning. So warning is based on the delay. So what is the warning is time 100, charge on node capacitor cap 1. Okay. So there is a charge on node capacitor that is of, that is a warning with, they have given because the charge is of more and the time delay is all about the 100. And then TREREG.V, this is the capacitor, that is TREREG capacitor 1 changes values of lags at simulation at 100 times. So at a simulation of 100 delay, okay, 100 times nanoseconds of delay at that particular time, the TREREG, the data type, it will change its value. Okay, for example, the data type TREREG is having some value as 0. After 100 seconds of delay, it may change from 0 to 1. That is what it's saying. And then 100 data, ST1, ST0, cap and LX. So here if you observe, this is a TREREG. Okay, TREREG is a resistive switch. It's a switch, data type switch. So we have given data. This is a gate and this is a NMOS switch. For example, if you're considering any PMOS switch. Okay, so this is what we observe by considering the TREREG switch. Okay, so this is about the data type and the decay. And now we will see the charge sharing example. So the charge sharing example is nothing but here if you observe there are two switches. One is NMOS and one and NMOS 2. So between these two we have the capacitors. So here the charge sharing, how the charge is sharing among the different switches, this is what the code is about. So module TREREG charge sharing, register ABC, wire X. Wire is nothing but a physical connection to connect between one switch to the another switch. This is a wire. And then TREREG large and TREREG small. So two data types that we are considering with respect to the large and small, TREREG large and Y, large and small, and we are declaring that data types with respect to Y and Z. So here declaration with large strength. So for the large strengths we are declaring it with Y. Okay, so this is a large strength, and for small strength we are declaring it with a Z. Okay, and then we will see that not X1. So this NOT gate, okay, this NOT gate is passing with respect to both the switches. So not as X and A, NMOS 1, NMOS 1 and NMOS 2. Okay, NMOS 1 is with respect to Y, B and X, and NMOS 2 is with respect to Z, C and Y. See, Z, C and Y, Y, X and B. This is with respect to 1 and this is with respect to 2. And then what we're doing is we are just initializing or after specifying everything with respect to the input and output and the connection between both the switches. And now finally we are initializing, okay, the mechanism how it goes here with respect to the charges, how the charges sharing among the switches is goes like this. Initial begin. Okay, when A is equals to 0, okay, when A is equals to 0, B becomes 1, okay, B becomes 1 and also C becomes 1. Then at 10 nanoseconds of delay, what happens is the C becomes 0 and A becomes 1. Okay, after 10 nanoseconds of delay, the C is, previous to the C is 1, right? But when you are applying some delay, okay, when some delay is considered, then at that particular time, the C becomes 0 and when the C becomes 0, A also becomes 1. Okay, quite opposite. Why? Because it's a NOT gate. Then, and at 10 nanoseconds of delay, when C becomes 1, B becomes 0. Okay, when C becomes 1, obviously B becomes 0. That means what? Here you can see a relationship between A, B, C, both the switches. Okay, both the switches A and NMOS 1 and NMOS 2, there is a kind of relationship between both two switches, and that switching on of two different switches is happening with respect to this NOT gate that you are considering. Okay, the charge, how the charge is transferred or how the charge is sharing among these two switches, and then finally goes with the end module. So this is about the problem solving that we can come across in the switch level modeling. Okay, so this is one of the best example. This is one of the problem that you that will arise. How the charge can be shared among the two different switches, and also we have discussed about the delay. Okay, how the delays are passed by between the different switches also, and as well as the signal strength and how the signals can be reduced based on the signal strength reduction, and as well as the signal contention. Okay, based on the signal contentions, we can able to know what sort of the signal is the weakest or the strongest. Okay, so this is all about the switch level modeling, a few problems based on the switch level modeling. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.